And welcome, function folks, for the first real lesson of the new unit, the exponential functions, and something that is called logarithms that we'll actually find out today what that's all about. The 3-minute review is actually a review from last year, but it might be a formula you're not sure of or didn't remember. This is a compound interest formula. Where A is the amount at the end, P is the principal or amount at the start, I is the interest rate per period, and N is the number of interest periods. So for A, FERD invests $200 for 4 years at 5%. And then, you know, how we do these is we figure out what A, P, I, and N are. $200 is the amount that FERD invested for 4 years, compounded annually. Now, since it's annual, then the number of interest periods is just 4. That's no problem. The interest rate, since it's annual, is 0.05. And remember, that word annual could be replaced by things like semi-annual, quarterly, monthly, all that business. And it will later in the chapter, but we're just getting going here. And now we just fill this in, pound it into our calculator, no problem whatsoever, easy peasy. Pound that in there, and you get $231.53 approximately. So hopefully you got that one in closing sentence. And whatever, how long would it take for his money to double? So sounds like we're interested in finding N here, where if I just write down the unknowns, he starts with 200 and we want it to grow to 400, right? That's doubling. I is still the 5%, 0.05, but N is unknown now. And so when I put this into the formula, N is what I want to find. How do I get the N alone? Well, I'm going to try some operations. Divide both sides by 200. Different color maybe. Divide both sides by 200. That cancels, and I'm left with 2 equals 1.05 n. And how do we get the n alone? Right? We need the operation that gets the n alone. It's not the nth root. Remember, if it was this sort of thing, the unknown is the base, right? Here, the unknown is the exponents. The opposite operation here would be square root. Those two are inverses. The problem is we don't know the inverse operation of an exponential function. We don't know the inverse of an exponential function. And in this case, the base is 1.05, but in general, this is true. We don't know what the inverse is of an exponential function. And this was the case in grade 11 as well, but how do we do it? Basically, we guessed and checked, right? So it was a pain. This was such a pain. Some people are good at using their calculator. Good old Mr. Restall isn't. But when you mess around a little bit, you'll end up trying to find a value of n that gets this as close to 2 as possible. So for instance, try a few. 14 is a little bit too low. I'm looking for this to be 2. 15 was a little bit too high. And if you fart around, eventually you'll get pretty close, but not exact, right? This is 1.9993, and that's pretty close, but this is no fun. There must be a way to do that, and we're pretty close to that right now. By the way, then the answer is it'll take about 14 years for it to double. So what's the whole issue? The issue is we don't know the operation that gets the n out of the exponent. So for instance, we know lots of inverses. Like last chapter, we were able to solve questions like this, right? If I wanted to find out the angle when I had a sine function, then I knew that the opposite operation was the inverse sine, which is just a button on our calculator, right? Well, what's the operation here? We don't know. What's funny is we kind of do, because if and we did this one yesterday, but it's worth redoing. And so this is a nice big copy, so you can make a nice big graph. This is easy to graph, right? We know this from grade 11. The point 0, 1, and then the next point is 1 and the base, right? 1 and the base is 1, 2, and then I can actually put a couple more points on here too, just because the base 2 is easy to get. Certainly this point, and also the -1, right? Remember, if I had 2 to the exponent -1, the negative exponent means for you to flip it. Negative exponent means reciprocal, means flip. And so then I get -1 and the flip of the base. That point there is -1 and the flip of the base happens to be 2. And then I can get my nice shape. In fact, just because the base is low, I can actually fit another point in here. This is the point 3, 8, right? Because this is just 2 to the exponent 3. And then I can get my exponential graph. Dandy. Easy. Review. But also, I could do the inverse, right? The inverse is just the reflection in this line y equals x, and then I can reflect these points. And, you know, it's just across the aisle here. And notice, if that's hard for you to sort of see, basically you just switch the order of the points there. This is going to be, instead of 0, 1, this is the point 1, 0. Instead of the point 1, 2, it's the point 2, 1, and so on. Instead of 2, 4, it's 4, 2. And then this point that was -1/2 is going to turn into 1/2 -1. That's the point 1/2 -1. And look what happens when I reflect that is I end up with, instead of an asymptote on the negative x-axis, it's an asymptote on the negative y-axis. This kind of makes sense because x becomes y becomes x. It's all good. 4, 5, 6, 7, 8 there. 3 was this point, right? This is the point 8, 3. And this is the inverse of that. This is y equals the inverse of function of f at x. Well, hang on a second. Weren't we looking for the inverse of an exponential function? Yes, we were. So this red function, we don't know the name of it yet, but we know it's the operation that undoes the exponential function. This red one is this new mysterious graph, that this operation that we're interested in. And you know, now it's time. It's a big day today. A new function. It'll be a new button on our calculator too. This is called the logarithm function base 2. And that's what we're talking about today, the logarithmic function. In the warm-up, we got stuck when we were solving equations such as this, right? We need the inverse operation of the exponential function base, not base 2, with base 1.05, right? So change that. That was a typo. And it says see notes on previous slide, and we'll get to that. So this here is actually the log function base 2. And we show the base of a log function base 2. We show the base of a log function as a subscript. So if I were writing this nicely, the 2 isn't sort of at ground level, it's a subscript, it's down here. And that's how we show the base. And we're going to point some things out about this graph soon. So for instance, what's the domain and range? The domain, well, is all the x values, right? X is got to be greater than 0. The range is all real numbers, right? It goes all the way down this way, and eventually it'll get all the way up that way. It's all real numbers. Well, remember that if I were to say the domain and range of this function, the domain was x is a member of the reals, and the range was y has to be greater than 0. right? And remember, the inverses, they change. The domain becomes the range becomes the domain. Nice. We'll talk more about aspects of this log function when we talk about graphs, because now basically this is a new basic graph, and we have to be able to do transformations to it. So we will, but that'll be later. Let's talk more about this idea of a logarithmic form. You know, we're used to this. We're used to exponential form. But essentially, we could write the exact same thing, if we wanted to, in what's called logarithmic form. Notice the connections. The base here is 2, and there's the base in this form. Notice where the exponents is. The exponents are, rather. Here, the exponent is in that familiar form. For the log form, it's the output. It's what comes out of the log, a log. So, in essence, you know, you're asking, well, what is a logarithm? I don't get it. What's a logarithm? A logarithm is the exponent. Logarithm is the exponent. And notice the last thing that we're interested in is what we would kind of call the output of the exponential form is what I call the power. It's like the big number. The big number is on the inside of the log function. This is kind of like the power. And it says, and the two forms are equivalent. So we can go back and forth between exponential form, which we're familiar with, to this new log form that's brand new for us. And in doing that, we're going to actually see this will lead to us being able to solve some problems. Okay. Do we want to get into the examples? How am I doing for time? Okay, I'm going to stop. We'll do the examples in part 2.